Now, in this last section, I want to show you what traces of life we find in these ancient sediments. This is what you want to hear. I've made you wait a whole lecture, giving you all the background detail, but now you understand the environment, you understand how the signatures are preserved, what we have to do to try to identify them, study them. And so let's go for it. Again, I just repeat, we only have 2 areas in the world where these signatures are preserved. So we just, I'm going to show you examples from Australia, from the Pilbara region, and an example from Barberton in South Africa. And what kinds of signatures do we find in these rocks? Well, we find signatures of chemotrophic organisms. These are organisms that have the most primitive types of metabolism. They're organisms that obtain their energy from carbon, from minerals, from gases such as hydrogen. Their carbon source is either from carbon, again, sorry, Frenchism there, carbon or carbon dioxide. But then we also see evidence for phototrophs. As I mentioned before, phototrophs have a more evolved metabolism. They probably appeared on Earth later than the chemotrophs. They obtain their energy from light. They form biofilms and mats, stromatolites, these 3-dimensional structures, and they can also be found in the planktonic, in the water column, in the upper layers of the water column. They need light, so they form only where there is sufficient light. And these are the main organisms. Now, I'm going to start off. Phototrophs are easier to identify because they form physical structures that are difficult to mix up with something that's abiological. So I'll start with the easy things first, and then we'll go on to the difficult things. Again, the strategy, always, you go to the field. You go to the field, you look at your geological environment, you study the rocks, you take a specific rock from a specific environment because you think this might be an environment where there might be traces of life, if that's what your aim is for. You decrease you increase the magnitude of observation. You look at things microscopically with the various electron microscope, various types of microscopes. You look for morphological features. You look for colony features. Going down to the molecular level, you can look at the bioorganochemistry, biogeochemistry, up to isotopic fractionation. So you use all of these. And I'm going to insist on the importance of field context, because when I first arrived in France, I was talking to I won't mention any names, but I was talking to a famous geochemist. And I said, I have some very nice samples from the early Earth that are well characterized. I know exactly where these samples come from. And he said to me, oh, that's fine. I don't need your samples. I have samples that somebody else sent to me. And these samples that somebody else had sent to him had not been properly characterized. And he said to me, you geologists, you can do the field work. We don't need to do that. Those were the implications of his words. We don't need to do that. We do the real work. We do the geochemistry. Well, he made some mistakes in his interpretation. Okay, so this is really important, and it's not just because I love going into the mountains that I do this. You have to believe me. So we have the environment. Again, another Frenchism. Oh dear, sorry. Anyway, we have our environment. We're in a shallow water environment, coastal environment, volcanic sediments, hydrothermal influence, just to remind you, in case I hadn't really brainwashed you with this. So let's have a look firstly at the evidence for phototrophic life. So the environments where phototrophs could form, they can form in the beach environment where there's light and water. They can form in the ocean column eventually. They can live in the ocean column close to the surface where the light penetrates. They can form on the surfaces of the sediments or even volcanic rocks if they're in the light zone. And they can form also around the hydrothermal vents if it's in the right environment. The only criteria is they need light. They need light. So there's quite a variety of environments where they could potentially exist, and in fact we do find them there. Again, to put you into the scene, lovely view of mud flats. I think this is in North Germany, actually, mud flats. And if you, as I mentioned, if I showed you, if you take a spade and you go through the mud flats, you can see different layers. But in this case, if you take a spade and cut through the mud flats, you can find layers that correspond to layers of mats, microbial mats that are formed by phototrophic microorganisms, all the layers that are sticking out. This is work done by Gisela Gelders in the 1980s in Wilhelmshaven. And she studied the microbial mat formation in this kind of environment. And we will also see something similar from the early Archean. So you can see these layers, very, very striking layers formed by the sticky microbial mats. And if you increase the magnification looking at these microbial mats, you can see that they start getting filamentous and they form a sort of wispy, wavy, up and down type of structure. This also can get preserved, and I'll show you some examples. So this is just to set the scene. Now, this is a thin section of a rock from Barberton. We have a thin section of the chert that I showed you from Barberton, the Joseph-style formation. And it's what we see here is a sort of dark layer that's quite dark, spotted dark, and also a bit of current controlled sedimentation here, some ripple mark, very fine sediments. But what I want you to have a look at is this dark horizon here. There's a definite horizon, and if we zoom in on that horizon, we see that it's coated with a very fine, filmy layer that's formed of different packets of very thin films. The scale bar for is 200 microns. These films are about 10 microns in thickness. They're very thin, but just look at them. They're very thin, wispy, wavy. They coat the underlying bed forms. They're not completely parallel. They include various other objects that are trapped in them, and they're very similar to these bed forms, these microbial mats that we see on modern sediments in the photic zone today. Now, these can be seen in thin section. They obviously formed on a sediment surface, and they were coated by more sediments, so we know that they're in situ. As I mentioned, syngenicity is important. Now, from the same rock exposure in another sample, I found on the surface of the rock, the surface coated with this kind of filmy substance, which has a definite orientation, and in fact, there are different layers of these filmy substrates. There also seems to be curling up. And in actual fact, what we're looking at here is one of those microbial mats, photosynthetic microbial mats, that was desiccated and exposed to the atmosphere. I'll show you evidence for desiccation. And it's formed of very fine filaments. If you look at looking at the scanning at this structure with the scanning electron microscope, we can see definite filaments that have the same width and and are quite extensive. They're less than half a micron in thickness, and they're thickly encased in kind of film mucus-like substance. And all of this is silicified, but there's organic carbon in it, and I'll show you the organic carbon later. So this film is formed by filaments, as in modern photosynthetic mats. They're associated with very thick layers of of mucus, of polymer, as in modern photosynthetic mats. Remember I showed you the modern photosynthetic mat from Shark Bay? Well, this one also has cracks in it. There's even soft deformation, tearing as it's drying out. These are features that cannot be formed by something that's already lithified. It was still soft. This is soft deformation, plastic deformation. So these mats were periodically exposed to the atmosphere. And not only that, but we get a suite of evaporite minerals. These are pseudo-evaporite minerals because they've been silicified, but we get a suite of evaporite minerals that are embedded in the surface at the different layers of this mat. And the evaporite minerals include pseudomorph gypsum, aragonite, halite, and high magnesium calcite. And they're embedded. You can see, I think here you can see a filament overlying one of the grains, and here as well, and in other layers you can see different layers. So we're definitely in, we know we're in, apart from the sedimentological features, we know we're in a very shallow environment, possibly a beach environment. Now, because we have such a well-preserved, relatively large structure, this feature covered about 6 square millimeters on a sediment surface where it was exposed. We can actually do some detailed work on this. And I'm going to go into some detail to show you the kinds of analyses that we can do to look at the different kinds of biosignatures associated with this feature, because this is what we can do in a laboratory here on Earth. Think about trying to do something like that in situ robotically on Mars later on. You'll see it won't be possible. Anyway, so one way of, there are a number of ways of studying this feature in more detail, because it would be interesting. We're lucky to have such a well-preserved structure. We can dig into it, have a look at its vertical section, do mini stratigraphy on it, compare it to modern microbial photosynthetic mats. We can take slices out of it as ultra thin sections for observation with the transmission electron microscope, for observation with the scanning electron microscope, synchrotron, nanosims analyses. We can do all of these things to document the biosignatures. So first of all, let's have a look at the morphology of this feature. So we're looking here at this wall. The scale bar here is 10 microns. So we're looking at this wall here. First of all, artifacts. All this pitting on the surface is because the way to cut into this material, we're looking at material that's silicified. So we use a gallium beam to sputter, to cut slices through the rock, and it leaves pits. So these are artifacts. But you'll notice that there's a surface coat of a light greyish colour. The scale bar there is 5 microns. So it's possibly 200 nanometers or so thick, underlain by sort of slightly darker grey layer, and then the bottom is sort of granular. But you'll notice also that there are these spikes cutting into the bottom. What are they? The matrix, the matrix of all of this is silica. Everything's been silicified, recrystallized to microcrystalline quartz. What we're seeing here is the quartz matrix, and these are the quartz crystals that are cutting into, as they recrystallize, they actually disturbed the base of this feature. So they're cutting into it. So we know, that this feature formed before the silicification and the metamorphism. More details. We take a slice of this material, and at the top of the slice we find these pseudomorphed evaporite minerals. In fact, this is gypsum. We notice a portion of the silica coat, and here in this particular case where we took a slice out of the structure, because of the drying it had lifted up from the base, and silica had coated the under part of the structure. The very dark grey areas are almost pure kerogen, and they're two locations, mostly the top of the feature and a little bit down here. This is pure kerogen, and in actual fact, keep in mind with photosynthetic microbial mats, they are stratified structures. The top layer it consists of the active organisms. These are the active photosynthesizers. They're the ones that are creating the biomass. Underneath, where you have the photosynthesizer, you have the dead organic matter from the photosynthesizers. You have the heterotrophs. They are living off. They are oxidizing the organic matter. This is what they're living off. So these features are very stratified on a micron scale level. So we have the top layer of kerogen here, and you'll notice that the bulk of this feature is sort of light grey granular, and it's actually carbonate. It's aragonite, and I'll go into more details there. And finally, right in the middle, there are some tiny grains, floating grains of quartz. Remember, these features are sticky. We're looking at polymer, which is sticky, and detrital grains stick to it and are entrapped by them. So we can study, in fact, what's happening here, and I'll show you the details in the next few slides, is that this top layer of pure kerogen that hasn't been calcified represents what was the original layer of living organisms. The lower layer, which has been replaced by granular calcium carbonate, represents the layer of degraded organic matter that has been remineralized. It's been oxidized by the heterotrophs, and most likely sulfate-reducing bacteria. I'll show the evidence for that in the next few slides. And it's the metabolic. It's the effect of the metabolic activity of the sulfate-reducing bacteria that has created in situ calcification. All of this has then been silicified. It's impregnated with silica as well. Anyway, so this is the sequence of events. Now, in terms of analyzing the molecular composition of the organic matter, there are a number of methods that we can use. In this particular slide, I'm showing just one of the methods. It's micro X-ray adsorption near-edge spectroscopy, in which we've been looking specifically at the sulfur content of this carbon-rich layer. With the SEM, we can map the carbon, but here we wanted to look at exactly what are the kinds of molecules that we can still detect in this matter. And in fact, the kinds of molecules that we can detect are heterocyclic molecules, i.e. extremely degraded organic molecules. This tells us that this material is very old. It's already and also the Raman spectrum signature says this organic matter has the same maturity and age as the rock in which it's found, another indication for syngenicity. But we find the molecule thiophene. This is a sulfur-containing molecule, and this molecule indicates that the organic matter here, the kerogen, the degraded organics, have been enriched in sulfur. They've got more sulfur than in the living organisms, and the enrichment in sulfur is due again to the activity of the heterotrophs, the sulfate-reducing bacteria, liberating the sulfur, and it's being concentrated in this area. We can also have a look at inorganic sulfur in the form of sulfate, and there is a little bit of sulfate associated with carbonates here. Again, another indication that we're probably dealing with the activity of sulfate-reducing bacteria. And I'll note here Laurence Lemel, Alex Simiovici, the ESRF in Grenoble. These are people with whom I've done this work. I've also used TOF SIMS on this material. Now, Hervé spoke about TOF SIMS yesterday with respect to the Rosetta mission. And the TOF SIMS, I haven't, again, because of my computer problems, I wasn't able to insert the slide. But the TOF SIMS of these samples indicate again that the organic molecules that are in this rock, associated with the organic matter in this rock, are basically polyaromatic hydrocarbons, PAHs. These are very degraded molecules. And they are, just like thiophene, these are molecules that are found in abartic organic matter in meteorites. However, there's a difference in terms of the distribution. Abartic organic matter in meteorites has a very, very broad molecular distribution. And in the Toff-Sims analysis of the organic matter of this particular rock, the molecular distribution is rather restricted, which is more similar to organic matter issued from biological materials. However, this underlies the difficulties of dealing with very old material. And remember, this is on Earth with top-level sophisticated equipment. And later think, how the hell are we doing this on Mars? Okay, so we're going to have a look at the calcified part of this feature, this mat-like feature. And in actual fact, I mentioned that it's very granular, and this is a TEM TM photo from that granular structure. You can see it's got a sort of network. There's a lot of carbon still in it, but it's got a kind of network texture, which is typical for degraded organic matter. But if you look very closely, this is work I've done with Barbara Cavalazzi and Caroline Andreazzi in Orléans when Barbara's there. We can actually detect why this material is so granular. We can find nanocrystals of carbonate. In fact, it's aragonite. They're very small. They're 3 to 10 microns in thickness. And they are embedded in this kerogenous material. And this is very interesting because, in actual fact, aragonite is not a stable mineral under general atmospheric conditions, and it transforms naturally into calcite. Here we're looking at a feature that's 3.3 billion years old, but there's still aragonite there. And the reason for that is that everything was almost immediately silicified, permeated with silica, which froze every single thing in time. This